Kyoto University, who will talk on matrix models for non-commutative rational functions. So please.
Okay, so thank you very much for the introduction, and I'm very happy to have a chance to speak at this seminar. So I will actually talk about this joint work that was put on archive recently about matrix models. Actually, I should say maybe rather random matrix models for non-commutative rational fractions. And so this is a paper which was written by 5 people, including myself. So maybe I should introduce a little bit the people. Initially, I was thinking about this problem during the master's studies of my master student Akihiro Miyagawa. And I also have a PhD student here in Kyoto, Felix Parot, with whom we casually discussed the question. And he mentioned us that actually at an Oberwolfach meeting the previous year, Roland Speicher had mentioned this question as an open question. So we discussed with Roland Speicher, and so Roland Speicher told us that since we were more advanced somehow, we could just think about the results. But then when Akihiro Miyagawa presented his results during his master's graduation, our results, so many people participated. There was a meeting here in Kyoto, and we realized that actually it was possible to combine results of Tobias May, who had been working with Speicher, and Shengin, who was also a former postdoc fellow of Speicher, and who is actually now in China. So we just joined forces. So yes, and so I will start with an introduction, maybe. Because I had somehow to, so my background is more free probability and random matrix theory, and I'm not an expert in non-commutative geometry, and actually even in non-commutative rational fractions, I'm not really, I mean, I only started to learn about this recently. So I think that it would be relevant in the context of this seminar to start with an introduction about relevant motivating questions. So if I start with very simple notations, so let's say that these are the polynomials. Okay, so let's say these are the polynomials in one variable. So this is an algebra, and I can embed this in the algebra in the field actually of rational fractions. So these are the rational fractions. So all this is completely algebraic, but we could decide that we would like to do some analysis about this. And here, like now, many things which could be done, but maybe what we could say is we could say, well, okay, let the polynomials act somewhere. Maybe let them act by multiplication on the subset of the complex set, or even on the real set line. So let's say that they act by multiplication on a segment, for example. So let's say that they act on L2 of 0, 1, something like this. Okay, let's say. And then what in this case I can see that the rational the polynomials, they are actually in this context they can be embedded in the bounded functions of they can be viewed as a bounded functions. So like this. And so a question, and of course, if I take a rational fraction, as soon as it has a pole inside 0, 1, it won't be a bounded function. But the question is, can I do something about that? And the answer is that we can do something about that if we take an unbounded operator perspective. So what I will here just say, I don't know. Well, maybe I don't want to tell too much about general unbounded operator theory. But let's say it's so here I'm going to consider just a collection of measurable functions. Of measurable functions, so they are almost everywhere finite. These are measurable and almost everywhere finite. And well, the point is that this is an algebra. This is also an algebra, and in this case, I can always succeed in doing this this embedding. It's and so the question is to see how far we can extend that somehow. So this is our motivation. So so here it was just I just did it for polynomials, but it would be more relevant for us to do it for a group. So now let me take G to be a group, and I am going to take the group star algebra. So C of G. So this is just the span of lambda G for G in the group. So this is just it's just G is just the basis, and then I give it a star algebra structure by lambda G. Lambda H is lambda G H, and lambda of G star is lambda of G inverse. So now I have a unital star algebra, a unital star algebra. And if I just copy basically the same reasoning, for example, I can check immediately that, for example, I can very easily, let's say, for example, if I take just the group on the free group on one generator, if I may say, I can also do the same. So I have this star algebra, and this star algebra is contained in a field. So here I don't know what. Maybe what I will do is I will use a notation which might be not standard, but which I will use, which Speicher introduced and which I would use afterwards. So this is something like this C with a notation like that. So this is so this here is a field, okay. Okay, and embed this. So I can just repeat the very same thing. So I can embed this in so in L infinity of the circle, and this one I can embed in L0 of the circle. So the question is, by the way, so here what maybe a simple remark is that here I can easily check by hand that this can be done for any, so this is okay for any torsion-free abelian group. This is just doing some rational fractions basically, and of course if there is torsion, this cannot work because sorry, I have a technical problem. Yeah, so work because then I will have a spectrum, and some non-trivial elements will fail to be invertible. So the question is, what about more general groups? So what about more general groups? More general, and here, of course, I mean non-commutative groups, non-abelian groups. And as far as I can tell, the first results in, or maybe one landmark result in this direction was due to Linel, to Peter Linel in '93, and he proved basically that this is okay, for the free group, So this is the free group on the generator. This is the free group on the generators. So what he has, but for this I should introduce 2 or 3 notations. So what do I mean by okay here? So one thing is that if I take the star algebra of the free group, I can embed it in its von Neumann group algebra. So this is the von Neumann group algebra here. This is the von Neumann group algebra. And well, so then the question is, can I embed this unital star algebra there in a non-commutative, in a skew field? So can I, in a skew field? That's the first question. And the second question is it possible to somehow view this as a non-bounded operator? So here the question is what to put here and what to put there. So here there is a notion which has been very well studied by many people. So there is, I think probably it started with Kohn and many others. So in an algebraic study of a universal skew field in which C of FD embeds. Maybe I will say a few words about it. I think it makes sense. It would make sense. And then once we have this, can we realize this as an embedding? So here, of course, I need to define what I put instead of here. And here, the correct point of view is the notion of affiliated operators. So I would take the same notation L0 F of D, and I would just say what I just write down what I mean. So this is the affiliated. So this is the operators affiliated to the von Neumann algebra, which is here. So the thing is that you can always define unbounded operators. Maybe I should say unbounded operators. We can always define them, but thanks to the fact that we have a finite von Neumann algebra there, this keeps a structure of star algebra. So this is a very pleasant object to work with. Actually, it's in a sense it has a behavior. It's not commutative, but it has a behavior which is close to that. And it turns out that that we have this kind of embedding. So there is this very beautiful result by Peter Linel, which I suppose was some kind of inspiration to us. I have to confess that I'm not an expert in the, in the proof. I think actually this is very non-commutative geometric proof with K-theory. This is related also to the Atiyah conjecture. So just one remark here is that again it is very crucial that the free group be torsion free for all this to be true. For this result to hold. If it was not torsion free, then so we want this property that the function somehow be almost everywhere finite. So if it's so if there is torsion, then if I move around my function, then it will have a kernel, and I cannot anymore define the inverse, at least in this analytic sense. And here I would like to make a remark also, which is I would say a remark as a probabilist, so which is my original background. So what this result from Peter Linnell implies is that for any self-adjoint polynomial which in non-commutative in the D generators of the free group and its adjoints, then what we have is that if I look at the spectral distribution of it, so maybe I should define it in 1 second if it's not obvious. So this is a probability measure on R. Okay, maybe I will just say it for now. This is the spectral distribution, which is a probability measure on R, compactly supported here in this case, probability measure on R. And what we have is that this is either some atom or atom free. So it's this is an atom if and only if P itself is trivial, is a multiple. I mean, if and only if P equals alpha, and in all other cases, this is atom free. Which, so yeah, maybe I should just say, okay, just in case it's not clear, let me clarify what I mean by this. This is the measure which satisfies the property that integral of x k d mu x equals tau of p to the power k for every k, where tau itself, tau is just a canonical trace. Tau of delta lambda is, they call it delta. Sorry, lambda. But sorry for the notation. Lambda g is delta g. Okay. And I personally, I find this result very interesting from a point of view of probability theory, because I can think of it. Let's say for example that P has positive coefficients, has non-negative coefficients, and that they add up to 1. Then we can understand this mu as a probability of return to 0 of a random walk on the group, on the free group actually. And this result says that as soon as we don't have this trivial walk which drifts away deterministically, then its return probability is atom free. And the truth is that I think that until maybe, so this was known for what, maybe close to 30 years at least. And I think that there was no proof, like no probabilistic proof available of this result until very recently. And even nowadays, there is an entropic proof by Speicher, May, and others, but like no real direct proof. So somehow it's a probability. It's a classical probability theorem, if you want, that whose proof relies on deep concepts of non-commutative geometry, which is, I suppose, an interesting feature. Okay, so yeah, maybe I should say one word also. I will keep using this. Maybe I should say one more word about this. How to define this. Maybe I should define the non-commutative rational expression, non-commutative rational expressions. And the way it works is basically this is any, maybe I should say any, I will just be a little bit well, hand waving, but probably in an obvious sense, any legal, legitimate expression in, well, first of all, d abstract variables, x1, xd, and then addition, multiplication, inverse, and parentheses. So, I mean, I could give examples, but you know, I can give as many examples as desired. So maybe example. Oh, and yeah, sorry, I should also add the complex number. So, for example, 2x1, x2 inverse plus x3 cube inverse minus 4, whatever, something like this. Okay, so all. Of course, I suppose I don't have to. I mean, when I mean legitimate, I should be careful how I do my parentheses for it to make a sense. But in principle, something like this makes sense. And then what one has is that on this collection of non-commutative. So first of all, we define. So maybe we call them R. Okay. So we call R such an expression. So this is R. And then what we have is we have a domain. We have the domain of R, which is the collection, which is basically all D tuples of matrices where this is well defined. So, for example, here at the very least, I would need to take x2 invertible, and then I would need to take this sum invertible. So basically, the only hurdle each time is when I have inverses. My only new hurdles come from inverses. Apart from that, I don't have a problem to define things. And so the domain is here a subset of the disjoint union for n, let's say bigger than 1, of d tuple of matrices mn c power d. So this is just a subset of this disjoint union. And then what we do is we define an equivalence relation. R1 is equivalent to R2. Well, okay, we define a relation if and only if on the set of rational expression, if and only if the evaluation of these two non-commutative rational expressions is the same whenever A belongs to the intersection of the domains. Intersection domain R2. So you see here, I really have to make an intersection because if I wanted to be mean, of course I could, I could do something like this. I mean, it would be legitimate to say plus x1 inverse minus x1 or whatever. Okay, and then I would change the domain, but it would still be the same, right? So I have to take into account these facts and some slightly less trivial facts when I do this. And this, as it turns out, is an equivalence relation. And when I quotient, I obtain this object here. The fact that there is an injective, I mean, the fact that it embeds in all this, I mean, there is a little bit of work to be done, which was done quite a while ago. But all this is well identified algebraic results. Maybe I should just make one more remark as well, that somehow here I really want to take the union of all n's. So if one does some topology on an algebraic sense, this is maybe not so convenient, but this cannot be avoided because, so maybe I would just write like this: large enough is important. And the reason is that there exists some non-commutative polynomials which which vanishes up to as long as you want. So I will just give an example here, which is this one. There is this famous polynomial which has a determinant shape source form. So I take the sum over all permutations on 2n elements of x sigma 1, x sigma 2n, and with a coefficient which is given by the signature of the permutation. And what is known is that if I take this rational expression here, this polynomial, as a matter of fact, this is 0. R is 0. So R A is 0 for any A which belongs to some d-tuple of matrices M Mn of C for n less or equal than n. So one has to be careful. I mean, you see, the inverse of this makes sense. It's easy to say that this makes sense, but it doesn't make sense if n is too small. So there is this warning which is going on here. Okay, and so the problem. So after this lengthy introduction, our problem somehow is to approximate. So we would like to approximate the group. So for us, actually, so for us, the group, the only group about which we can say is a free group with finite dimensional objects. So here, yeah, maybe let's see. Maybe I should mention this this famous related problem. So There's this famous related problem. So which is so if I given a group G which is generated by let's say D elements G1 GD, can I find can one find unitaries G1 G1n GDn? So unitaries, let's say n by n unitaries, n by n. So maybe, yeah, okay. Does not necessarily have to be the same n, but let's put it that way. Unitaries. So this is unitary matrices, such that for any word for any element, for any word actually, we have that this pointwise approximation that holds 1 over n trace of the word applied to the GIN converges to the trace as described before of W of GI. So so this is actually true if and only if. Well, I mean that's a definition basically. The group G is hyperlinear, and it is an open question whether all groups are hyperlinear. So this is very closely related to the cone embedding problem, which has seemingly, which I suppose has been disproved recently without solving this question. Just one quick remark here. So this is again like some kind of motivation, but a remark, a very simple remark, is that if G is residually finite, then of course this is possible to do it. Well, we just take our sequence of quotients and we obtain the desired unitaries here. So the thing is that somehow this observation solves the problem for polynomial approximations, but this observation, does not solve the problem at the level of the skew field of G. And well, the problem is that if I take finite quotients, then I have torsion. So I cannot handle that. So this takes me finally to my motivation somehow, to what we try to do. So there is so the thing is to take a random approach, and what here I want to do is to quote very famous results of Voiculescu. Voiculescu 92 maybe. And his result is that if I let U1 and UDN be IID hard distributed random unitaries. So UN is a compact group. Is the n by n matrices, the n by n unitary matrices. So it has a unique left and right invariant probability measure, the Haar measure, and then let me take d independent copies of it, which I call U1n, UDN. Then what Voiculescu proved is that if I look at again if I take any word in the UI and the UI in D generated of the free group and their inverse, then if I look at the normalized trace of my word evaluated in the UINs, then this converges as n goes to infinity towards the trace of the words in the UI. I mean, I should also have a UI star here, right? I'm doing it with the inverses. As n goes to infinity, and this is almost sure. This is an almost sure result. So so this was so Voiculescu actually called this result asymptotic freeness. Asymptotic freeness. And the conclusion of it. So I think I introduced this notion. Sorry, I think I introduced this notion of So I introduced this notion of law here, which I will continue, which I will reuse again over and over from now on. What this implies, what this implies in particular is that for every non-commutative polynomial P, self-adjoint non-commutative polynomial P in the group star algebra, the free group, if I evaluate it in the unitaries, then the law of this converges, well, actually almost surely, to the law of the limiting object P of the UIN. And here, this is the proof is, I mean, just follows from linearity and expanding and this pointwise convergence there. So our question, which hopefully by now is makes sense, strikes as something natural, is what about? So question: what happens in the non-commutative rational fraction case? So so here we can do it for this, and can we do the same? We do the same for P, which is a non-commutative rational fraction. And well, so what I basically our answer is yes. So the answer is yes. So theorem. The answer is yes. And to be more specific, this is so P for any P there for any non-zero p, p evaluated in the UI ends is almost surely well defined for n large enough. And what we have is that the law. So maybe I should just here I will take the best. I will try to take the best. Oh no. I will just try to take the best of both worlds, and this result here holds true as well. So the only thing that we have to be a bit careful about now is that this is not bounded anymore in principle. So we just have to modify appropriately. So the appropriate modification. Basically, maybe. So we don't. So the definition which I gave was through moments, but we can take a definition like a cumulative function. Cumulative function distribution definition. So this is the. I mean, this was our initial result, and actually we can do much more. So let me outline. Let me maybe state the more general results. But before I do this, let me make one comment. Which is that somehow the results above of Linel, they were all done initially. I think. I mean, as soon as we go non-commutative, I think everything, most of the things until what 4 or 5 years ago had been done only for in a group or in a group algebra context. Whereas, of course, I mean, here we are not talking about a group here. And actually, Speicher and May did quite interesting, proved quite interesting results. So so Speicher, May, Ying, and a few others proved that star-free semicircle elements embed also in a skew field. So basically, they prove that the same scheme holds, that there is on the one hand there is a skew field, and that all this can be viewed as non-bounded operators. So we don't have to only to take group elements or group algebra. This works in a much more general context, which is interesting because in random matrix theory, here we are dealing with random matrices. We are not only dealing with random unitaries, we're also dealing a lot with something which is called GUIs. So these people here, they are approximated by, in general, they are approximated by GUIs, approximated by something which is called GUIs, like Gaussian unitary ensembles. So this is something which is called Wigner's theorem. so the famous Wigner's theorem of the late 40s. So GUE is just a Gaussian distribution on self-adjoint matrices. So this is just a distribution that is exponential minus n over 2 trace of x squared dx with some constants, where this here is the Lebesgue measure on the 2D dimensional real on the n squared dimensional real vector space of self-adjoint matrices. So this is just some canonical Gaussian measure, and if I pick the matrices at random according to this distribution here, then they tend towards semicircle elements whose distribution is a semicircle between -2 and 2. So and one more thing is that, so here what we have is we have naturally some random matrices which involve inverses, and intriguingly somehow random matrices involving inverses are actually very common in applied mathematics, like in finance or in statistics. There are lots of random matrices which involve Wishart matrices and their inverses. So somehow each time to prove any kind of convergence, it was very painful, but somehow thanks to this global approach, now this can be done systematically. Thanks to the general result, which I'm going to quote. So the general result is the general result, which is basically, well, more or less the same. What we do is we take x1 n x dn. So and here these people are self-adjoint matrices, and in addition I take so maybe I will call them d1, and then u1 and u d2 and these ones are unitaries. And now I take, in addition, I take R non-degenerate rational expression in d1 plus d2 variables, and if so, then if the pair the d1 plus d2 tuple xi n uj n converge in star distribution. So every word, every non-commutative word in xi, ui, and ui star converge to some, let's say, xi uj, sorry, uj in a non-commutative probability space. So I didn't define a non-commutative probability space, but a non-commutative probability space is just a star algebra with a trace. And if in addition this limit satisfies regularity condition, which I'm just going to write without really explaining it. It's delta of x u. Sorry, I have some problem with my handwriting. Equals d. Then if I evaluate the rational fraction on xi and ujn, the law of this. So first of all, yeah. But okay. Sorry, I should say plus Rn well-defined. So the evaluation well-defined for n large enough. Then what we have is that the law of Rn converges to the law of R. So here I should maybe just clarify a bit that there is a notion in free probability of microstate free, free dimension, and this is basically this quantity here. So which actually in a hidden way encompasses the fact that there will not be atoms and a little bit and a bit more, but basically there is. So what it tells basically is that, well, we can really put apart. So this is really a matrix algebra result in a sense. I mean, this is just matrices, deterministic matrices, and as if they are well defined, then for free I get a convergence in of the distribution, and the well definedness is something which can be proved for typical random matrices, matrix models, quite in quite a direct way. So this is the main result, and maybe I have what do I have until so I have 5 more minutes. Is that it is correct? I suppose so. But so I will just give a very quick outline. An extreme somehow. I mean, the result itself somehow is kind of satisfactory from a point of view of random matrix theory and free probability theory, but the proof, as soon as as one brings the right tools together, is actually not extremely striking. So the outline of proof. I'm just going to give two main ingredients. So the first one is that for any non-commutative rational fraction, I can always write it like this. So this is it's not obvious, but this is a result. I can always write it like U A inverse V. Formally, I can always write it like this, where U and V are elements, just vectors, and A is a matrix. So is an M by M matrix, which does not have coefficients in C, but which has coefficients in the free group algebra in C of F D. C of F D. And even more important than this is that this here is of degree 1. Of degree 1. Lesser, actually, less or equal than 1. So what it says, so this is sometimes this is called the linearization. So in principle, you see that I gave a few examples by hand of a rational fraction. It can involve many nestings of inverses, sums, products, and again inverting and so on. So it looks quite involved in principle, but actually you can really, there is an algebraic result which says that you can really store the structure if you are willing, if you accept to pay the price of working in in an algebra in a bigger algebra of matrices. You take matrices with values in the group. Of course, like the inverse has to be somewhere, so we have one inverse. But it's very nice that we have just the inverse in one spot somehow, and somehow this left, this right V and left U transpose. You can think of it as looking at the corner of your big matrix. So basically, you take a big matrix of rank of degree 1, which means that it has some constant terms and some terms with values in the generators of the free group and its inverse, and that's all. Like no G1, G2, whatever, just GI inverse and constant terms. And then if I take M big enough, I take the inverse, then any rational fraction can be, has in its equivalence class an expression like this. And this is what we use, because once we have this, we can somehow, like here it's really going to be hand-waving, but the idea from there is really simple. In a sense, what one just has to do is, you see here one has to take the inverse. So let me plot the inverse function, and so this is the inverse function, okay? And what we do is we do a two-step approximations. We first approximate it like this. So maybe I have an epsilon here, minus epsilon here, epsilon there, and then I do some kind of approximation like this, and I try to explain why one has to try to explain why the spectrum is not too much affected by this. So of course there is an unbounded part, so a little bit of work has to be done, but it's not too difficult. And then this approximation can be approximated by some polynomial, and then once one has the polynomial approximation, then we are left with using what Voiculescu already taught us. So then we can use the almost sure asymptotic freeness. So then finally we use Voiculescu's result. So in a sense, it's a little bit maybe it's a little bit disappointing in a sense, because doing rational fractions exactly boils down to doing almost sure asymptotic freeness of random variables, as soon as we have the right tools. And yeah, well, it's I think it's about time, so maybe it's the right time to stop. So thank you for your attention.
Thank you very much. Any question or comments?
Yes, I have some paper to indicate, which might be very interesting with respect to what you are doing. You see, the point is the following. The point is that when you start with the first example you considered, which is the case of Z, where you have the circle, and then what you do is you take the group ring, and you take the rational fractions. Okay, now, so let me only consider those rational fractions which will be bounded, which means that I take poles outside the circle. But I mean, this is fine. Then it turns out that there is an old result of Kronecker, which goes back to the 19th century, and which characterizes the operators which are obtained in this way by the fact that their commutator, I mean, of course, one has to put it in modern language, but I mean, the characterization is the fact that their commutator with the Ilbert transform is a finite rank operator. Now, this is a very deep result because it was used by Borel then in his work by Emile Borel in his work on analytic functions. So it's a very deep result. It's not a trivial result at all. Now, it turns out that in my book, in 1994, I have extended the Ilbert transform to the case of free groups. And the way it is extended is rather simple to explain, because it is defined in terms of the action of the free group on a tree and the natural Fredholm module that you get from the simplicial complex associated to the tree. So if you want, essentially, what you have is you have the vertices and the edges. And if you fix a base point, you have a corresponding transformation from vertices to edges and conversely. And it turns out that this extends the Ilbert transform from the case of the group Z to the case of a free group of arbitrary number of generators. I mean, the main point being that it acts freely on a tree. Now, in my book, I did a conjecture, and the conjecture was that the result of Kronecker would extend to the case of free groups and would characterize elements of the skew fields that you were talking about. You know, it would characterize those which are bounded by the fact that among the C-star algebra and even matrices over the C-star algebra, the commutator with, I mean, the quantized differential, which is the commutator with this Ilbert transform, would be of finite rank. So this was a conjecture in my book, but it was proved positively by Gérard Duchamp and Christoph Rothenauer. And I mean, if I could share my screen, I could show you the paper.
Sure, yeah.
Yes.
I will stop.
Yes. So, Yoshi, if you can share my screen. Yes. Yes. So let me show you this paper. So you can see the paper. It's called Un critère de rationalité provenant de la géométrie non commutative. And I mean, so it's really a beautiful result, but it seems to be very related to what you are doing. Because I mean, what is going on?
Thank you very much.
You see. So I mean, you see, the point of all this story is that it gives you, in fact, a notion of differential geometry on functions on the, I mean, in the sense that, okay, and then this, it turns out that this result of Kronecker extends perfectly well, and it characterizes the rational functions. Now, so let me stop sharing, but it's important that you take the reference. It's Inventiones Mathematicae in 1997.
Thank you very much.
Yeah. So let me stop sharing.
Yeah,
and
I took it. Yeah.
Yeah. Okay. So you could take it now. So what I mean is that, you know, it's quite a nice result because it allows to put questions about differentials and so on, and also, I mean, the if you want, when one looks carefully at the proof of the result of Kronecker, it's really a very powerful result. I mean, Emile Borel used exactly this result when he proved the fact that if you take, so what Borel proved is that it's a beautiful result also. He proved that if you take a power series which has integer coefficients and which has, if you want, a radius of meromorphy, which is strictly bigger than 1, then it is a rational fraction. I mean, this is an amazing result, which has been used in the first work of Dwork on the Veil conjectures. So I mean, it's really, you know, very intricate and deep stuff, and I think it's quite worthwhile that you look carefully at the relation with what you do. I mean, yes.
Okay. Yeah. So thank you very much for this.
Okay.
I will definitely look into it. We are actually preparing a version 2, so this is it's perfect timing.
Yeah, great.
Thank you very much.
Yeah, well, thank you for your talk. I mean, the talk was very clear, and okay, I appreciate a lot. Yeah. But I got the notice of the talk very late. I mean, that was unfortunate, I think.
I'm sorry, it's my fault. I'm sorry.
Yeah, okay, don't worry. But I mean, so I was expecting to have the link. I looked everywhere in my email, I couldn't find it. So I was a little bit worried. But okay, no, that went very, very nicely, actually, yes. Okay.
Any other question or comments? Okay, so let's thank the speaker again. Thank you very much.
Thank you very much.